All right, so welcome everybody to Gilad's seminar. Gilad holds a BSc in Mechanical Engineering from the Technion, summa cum laude, from 2014. In the middle, before starting his MSc, he has been working in Rafael for a few years, and he has been pursuing his MSc in TASP since 2018. All right, Gilad, go ahead, please.
Hi everyone. The current seminar is about an approach we developed in Volmi, which concerns informative planning with high-dimensional non-parametric beliefs. We'll begin with an introduction. Now, autonomous systems. What is an autonomous system? A system can span from a small drone to a city and beyond. And for the autonomous part, we have many sub problems which are dealt with today in making a system fully autonomous, such as learning, perception, and decision making. And we will here focus on the planning part. So we more specifically want to deal with informative planning. For example, in exploration and search and rescue missions, we wish to map an unknown terrain, and we want to reduce the uncertainty of our state, which is the map. We have also sensor placement. We want to place sensors, a small set of sensors on a grid map, and to reduce the uncertainty of the rest of the grid map. And also for the localization problem, we wish to localize a robot and with a guaranteed amount of uncertainty. So the problem we wish to solve again is informative planning under uncertainty, of course. The belief space in this scenario is high dimensional, and the beliefs are non-parametric. And the contributions of our work are dimensionality reduction for evaluating uncertainty, which we will refer to as involvement. This concerns also non-augmented as well as augmented scenarios, which we will discuss further. And we also suggest a way to avoid the reconstruction of future belief surfaces, which we will refer to as SMC. And lastly, we show how these two approaches are applicable to belief trees. So the related work on this area, we have works which deal with planning with non-parametric beliefs, meaning the informative and high-dimensional parts are not of their concern. There are many works which deal with informative planning with non-parametric beliefs, but they do not scale probably to high-dimensional scenarios. And we have also works which deal with high-dimensional scenarios in informative planning, but they assume Gaussian distributions. These are works of Vadim's group, Dima and Chen. And there are also works which are related to specific planning and decision-making tasks, while our approach is general for the informative planning scenario. Okay, so we'll begin with a small introduction to how to account for the uncertainty of the state. So first, the state at time t is xt with dimension d. In full SLAM, for example, the state is composed of the robot's trajectory and the map. This can be, in general, high dimensional. and this is what this is an example of a high-dimensional state. We also have we can transition the states, meaning the probabilistic transition model is a function of the previous state, an action we make, and some noise, and it can also be viewed as a sampling, as xt can be distributed with the probabilistic transition model pt, which is conditioned upon the previous state and the action. We also acquire observations. The probabilistic observation model is described as such. Zt is an observation, which is a function of the current state, xt, and some noise. And due to this noise, again, Zt can be considered as distributed with some probability distribution Pz, which is conditioned upon the current state. Now, the history up to time t, we will define it as the union of measurements and actions up to this time. And the belief is defined as the probability of the state xt given this history. So beliefs can generally be represented as a factor graph. We will use factor graphs all over this seminar to try to be more coherent. These are bipartite graphs with variable nodes and factor nodes, which are probabilistic constraints. For example, we have here an example of a factor graph of a SLAM problem. The blue circles are the big circles are variable nodes. The small circles are factor nodes, which are the probabilistic constraints. And we here represent the belief of the state x0 up to 4 and L1 up to 5. For example, this factor here is a transition model, and this factor here is an observation model, and this factor here is a prior, which we did not discuss, but we can also have some probability, some prior probability over each of the states. Now, a toy example for planning, for describing planning, we have here on the right a drone which needs to decide between making two actions. On the left action observes these four landmarks, and the right action observes these landmarks. We have also many landmarks which are all representing the map. And the question is, what is the best action to make? So we begin with describing the framework of the planning. A POM-DP, which is a partially observable Markov decision problem, is defined by a tuple. This x, a, and z represent the state, action, and observation space of the problem. The belief of x0 is the belief at planning time, which is the prior. PT and PZ are the transition and observation models we have presented earlier, and R is the reward. So the reward in POM-DP is defined as a function of the state and the action, except for the terminal reward, which is not a function of the action. The objective function is defined as an expectation over the sum of rewards, and we wish in the planning process to choose the best action which basically which is the one which maximizes this objective function. And we know that our approach also supports a policy formulation, but for the interest of time, we do not show it here. Now, for the informative planning scenario, a suitable framework would be to use raw quantities. We just change, instead of the reward raw, the R, it is now raw. And raw is a function of the belief of the state instead of the state itself. And the objective function and the optimization problem is the same. We have just changed the reward. So changing the reward, it is now over the belief. This means that we need to evaluate the distribution's value at each instance of the state. And this entails basically a higher complexity, which makes ROPOM BP a more complex problem than regular POM-BPs. Now, solving the planning problem, the solution can be comprised of many building blocks. For example, the optimization method. It can be a belief tree or some variation of gradient descent. We also need inference method to infer into the future. For example, using factor graph methods or some particle filter methods. And lastly, here, as the last example is the reward evaluation, which is the focus of our work. We will discuss about the reward evaluation. So we need to introduce some information theoretic costs, which resemble the row we discussed earlier. We will begin with the most common one, differential entropy, or negative for the reward. Before getting an observation, it is an integral over the probability of the state, an integral over a function of the state, p of x log p of x. Acquiring an observation, it becomes this variation, which is just the same. It's just to take the probability distribution and put it inside in the right place. And for high dimensional states, this requires a high dimensional integration. We also note that every probability distribution is also conditioned here on history, and we do not show here just for readability. Now another reward we can use is information gain, which is the difference between the posterior entropy of after getting an observation and the prior entropy before getting an observation. And this is basically the amount of information gained by this observation. And we here wish also to discuss an augmentation setting. We use in our work for a smoothing formulation, which means that we take the new state xt, which is a function of the previous state and summation and the noise. And when transitioning the states, the new state xt is augmented to the previous. We do not discard the previous as in filtering. Some parts of the previous state might be marginalized out, and we here do not do this. But this is necessary only in the context of planning. We can do this in the inference level, but in planning we cannot do this. This is an assumption of our work that we use smoothing formulation. We might encounter this smoothing formulation, for example, in active SLAM. In Gaussian cases, it was proven that marginalizing out past states destroys the sparsity and eventually makes the problem less efficient to solve. Now, in short, we will denote the state, the prior state x0 as x, all the sequence of new states x1 to t as x new, and the successor state xt as x tag. Now, with this augmentation, we need to introduce some new rewards. For the entropy, this is not a new reward. We just say that the posterior entropy is already taking into account the new state. But for information gain, we need to define it otherwise. The augmented information gain, as you can see here, where is my mouse? Okay. We differentiate the prior state and the new state with this box plus operator. Why do we differentiate? Because x new only appears in the posterior entropy, and the prior entropy does not include it. This allows measuring also the uncertainty introduced by transitioning, which original information gain cannot do. Also, augmented information gain is a generalization of information gain. If we, for example, take x new as an empty set, then IG augmented and IG are the same. So the question is, which reward function should we use? For Rotman DPs, the prior entropy is equal for any action, and we can say that choosing a negative entropy or augmented information gain is equivalent, and we will work with augmented information gain because you'll see it further in the seminar. Now, lastly, for the introduction, we deal with non-parametric beliefs, which are usually represented with weighted particle sets. We have here high-dimensional samples of the state and the weights of these high-dimensional samples. And we have n samples. And in order to have sufficient resolution to represent reliably the belief, in non-parametric scenarios, it means to choose the number of samples n exponential in the dimension of the state, which is referred to as the curse of dimensionality. And just going here, I wanted to know that in SLAM, for example, when you acquire some more landmarks, the dimension of the state also increases in time. So our approach begins with a way to reduce the dimensionality for the reward evaluation. We get back to the toy example from earlier of a 2D drone looking from above and needs to choose between two actions. The belief again is high dimensional. There are many landmarks, for example, and it might observe only a subset of this landmark set. We'll refer to these landmarks as the involved variables, the blue landmarks. These, and the question is, can we solve the informative planning problem considering only the involved variables? Now, if we represent the problem with a vector graph, we have here a certain trajectory, x0 to x4, the blue variable nodes, and the green variable nodes are some landmarks which were observed. This is the our prior state. which involves already x01 to 4 and L1 to 5. We of course can have much higher dimensional states. And one action might look like this. In a factor graph manner, we introduce two new poses, which create some new factors. And these new factors basically involve only from the prior state. It involves only L3, X4, and L5. So this will be the X involved. And we note that the gray variable nodes here are X new, and they are inherently involved in the planning problem, so we do not discard them. For the second action, we here have also two new other poses, which introduce these new factors. And here the X involved would be X4, L4, and L5. And in words, the involved variables directly participate in generating future transitions and observations. And we know we already discussed about the transition observation models in a general context that they involve the whole state, but in general they might involve a smaller subsets. Xt-1 to Xt-1 transition is a subset of Xt-1, and Xt observed is a subset of Xt, and this will be taken into account as the involved variables. And X involved again is a subset of the prior state, and this involved subsets might be much lower dimensional than the entire state. So if we exploit the structure, or we are given what are the involved variables in our problem, for Gaussian beliefs, we already know that the information gain over the involved variables is exactly the information gain over the entire state. This can be seen in the works of in two works of Vadim, of Chen and Dima, which were on this group, and we note that for non-Gaussian distributions, this is not necessarily true. So let's consider a way around. We will get back to the objective function. It is an expectation over the sum of rewards, but we can also write it as the sum of expected rewards. And the question is, can we reduce the dimensionality for the evaluation of the expected rewards instead of the rewards themselves? So for the information gain, we have an expected reward which is called mutual information. It is just an expectation over measurements of the information gain. It represents the mutual information between the state and the measurement, which is considered a random variable as well. And it turns out that we have proven that the mutual information over the involved variables is exactly the mutual information over the entire state. And this is true for any distribution, not only for the Gaussian case. Integration here is done because the mutual information involves the entropy, then it has integration in here. So it means the integration is over a smaller subset of the states. And we also know that there is an underlying assumption here that data association is assumed to be solved at playing time. So if we want to show it in an information diagram, we begin with an entropy of the prior state, and we can split it to the involved, to entropy over the involved and entropy over the uninvolved. We here show the entropy of the measurement. The entropy is the areas of the serials, and the mutual information is the bound area, the gray bound area. Is the mutual information between the state X and the measurement Z. And we see that if we remove or marginalize out the uninvolved variables, these areas are the same. So now we again get back to the augmentation part. We discussed about augmented information gain. Now we introduce the augmented mutual information, which is again only the expectation over future measurements of the reward we have discussed earlier. And it turns out also here that the dimension, we can reduce the dimensionality for the augmented mutual information. We see here that the mutual information is calculated over the involved variables and the new variables instead of the entire state and the new variables. And the relation to mutual information is such that it is the original mutual information minus the expected uncertainty from the transition model. Again, in an information diagram, we are presented again as earlier. We have just added the entropy of X mu in green. We'll split it for a nicer view, and we see that on the left, the dark gray area represents the mutual information between the successor state and the future measurements. On the right, the light gray area represents the entropy of the new variables given given the prior state, which is the transition model. And we see that omitting the uninvolved variables again does not change these areas, and so we can say that the mutual information over the involved and the entropy given the involved is the same, and we get this conclusion in an information diagram. Now for our approach involve me, it is just an algorithm which uses this relation, which we have shown of the dimensionality reduction. And its basic framework is to determine the involved with some heuristic. We then marginalize out the uninvolved variables, and we finalize by calculating the mutual information over the involved variables instead of the entire state. And it can be used for any task involving mutual information calculation between two multidimensional variables, not only for planning, but we here use it in the context of planning. We also extend this by observing that marginalization might entail heavy costs. We can choose for a bigger subset X involved plus, which is between X involved and X. For example, if we want to do a one-time marginalization, X involved plus would be the union of the involved variables of each action. And we then get a more general relation that we can state that the mutual information over the X involved plus is the same as the entire state. And represented with a factor graph, the involved plus would be to just earlier we have taken for the first action L3, L5, and X4. And for the second action, we've taken L4, X4, and L5. And X involved plus is just a union of all of this. So to summarize this approach, involve me breaks the relation between the dimensionality of the states and the accuracy and the complexity of evaluating the reward. These are now dependent on a much smaller dimension d, this small d, and it means that in the non-parametric scenario, we will only need small n number of samples, which might be which is much smaller than than using the naive approach with big N. We also suggest another approach to avoid the reconstruction of future belief surfaces. The common approach to calculate mutual information is to go through evaluating the entropy terms. And these entropy terms should go through the evaluation of the posterior beliefs. And we have some estimators which first wish to reconstruct these beliefs, such as the resubstitution estimator. We have here, this is a sum over the particles. And we also here, this means a reconstruction of the belief, which is done, can be done, for example, with kernel density estimation approaches. And we would like to avoid future belief reconstruction because it might entail error. It might add more to the estimation error, and it might entail another level of complexity in the shape of hyperparameters, for example. Now, the mutual information, we have found that it can be calculated using only known models. The transition uncertainty, the observation uncertainty, and the normalization uncertainty, these three terms here. And the entropy of the normalization uncertainty is also calculated using the known models, and the integration is done over the involved variables. This allows us to avoid the reconstruction of future beliefs, and we then use it for our estimator. This relation, we use it for our estimator in ESMC. Its general idea is to propagate state samples in a sequential Monte Carlo SMC manner. We then generate possible future observation, and we then evaluate the models at these sampled instances, which is related to involve me because we inherently only need samples of the involved variables to evaluate the models. The complexity of this estimator is order NMD, where N is the number of state samples, M is the number of observation samples, and small d is the dimensionality of the involved samples, of the involved variable subset. And for example, if we use the resubstitution estimator with KD we have shown earlier, its complexity would be squared in the number of state samples compared to our estimator, which is only linear with the number of state samples. And also this is only true if we use the involve me on the RSKD. If we use it naively, the resubstitution KD, then we'll need much more samples, big N, and the dimensionality would be much bigger, D. We also note this estimator is an anytime algorithm. So we, if we want to add more samples to this estimator, we can do this without calculating from scratch. The last part of our approach is to show how involve me and MeSMC are applicable to belief trees. So the solution to the planning problem is obtained by maximizing the objective function. It can be also shown recursively. It is the Bellman optimality equation. And it is commonly solved with the belief tree. Here, this is the root. The square nodes are action nodes, and the circle nodes are observation nodes. From each observation node, we can calculate of each action node. We calculate a reward, an immediate reward, and finally it is solved by evaluating these rewards. And there are many methods which use the belief tree, and we want our approaches to be to cope with it. So the Bellman optimality equation, it uses a reward. It is shown with a reward, and our approach deals with an expected reward. And we already noted that we want them to cope together, to cope with the belief tree solvers, and this is not trivial. This is the goal of this section. So how can they cope? We remind that the mutual information over the entire state is equal to the mutual information over only the involved. And these are expected rewards. On the left, it is the expectation over rho t. On the right, it is an expectation over rho t involved. And we cannot state in general, as already mentioned, that rho t and rho t involved are equal without expectation. But it turns out that solving the optimization problem with any of these rewards is equivalent, although they are not equal. And so we just solve the planning problem with the involved reward instead of the original reward. And this also means that if we use the one-time marginalization we've shown earlier, it means that that during the planning process we maintain a low dimensional belief over the whole tree. The second question is, how can MeSMC cope with belief trees? We remind that MeSMC, it calculates directly the mutual information, meaning it does it without going through information gate. And up to now, it was treated in general as sequential. What do we mean by sequential? For example, the expectation here is over the sequential measurements, or the measurements from time 1 to t. We remind that 0 is the time, is planning time. And so naively calculating the sequential mutual information, it yields a degenerate belief tree. We have here only action nodes without observation nodes, and belief tree solvers do not cope with it, and so we would not want to use this approach. So we approach it in another way. Instead of looking at sequential mutual information, we look at consecutive mutual information, which is, for example, in here, you see the above mutual information is over the sequential future measurements, and the lower one is only over the last measurement and the last state, and given the previous state and not the prior state at playing time as earlier. So we just define a new reward, Roti prime, which is a sum of consecutive mi values, and the consecutive mi value at each time is just inserted into the MSc estimator instead of the sequential as we discussed earlier. And we also note that these rewards can be incrementally updated, so we do not have to calculate them from scratch. And solving the solving the optimization problem with Roti prime is the same as solving it with the original reward, and we just solve it. We just show it in here in a visual manner. And again, also here, if we use the one-time marginalization formulation with x involved plus, we also here maintain a low-dimensional belief during the playing process. Now for the results. Our scenario is 2D SLAM, which is created synthetically with a factor graph. We use Gaussian distributions for analytical solution. However, we note that it is treated as non-parametric. We use samples. We only sample from a Gaussian distribution. And we compare between three calculation methods: naive kernel density estimation, involve me with this kernel density estimation, and involve me with MSc with our estimator. And the KDEs were implemented with perfect inference in our implementation. So we first wanted to evaluate what is the impact of the dimensionality on choosing an action. We have here 4 different actions on the x-axis, and we see here the values, the mutual information values of each action. The dimension of the prior state is 150, and the dimension of the involved variables of each of these actions is constant. Is 4. We have provided 300 samples to calculate the mutual information, and we have run it 100 times to evaluate the mean and the standard deviation of the results. We see that the mean is pretty much goes through the analytical solution on the blue. You do not see it just here. It appears here. But we see that there's a very high variance in the naive KD approach, which means that if this is the true optimal action, and for one of the trials we get that these are the mutual information values, then this would be the chosen action in the naive approach, and this is not wanted. For the involve me approach, we see a much lower variance of the results, both in the KD and MSMC. And for MSMC, we see that we have a small bias compared to the KD, but we remind that the KD was provided with perfect inference, meaning that their samples were from the perfect from the true distribution. Now we wanted to check what is the impact of increasing the dimensionality on the accuracy. We here see only one action, and the dimensionality of the prior state is increasing. The dimension of x involved of this action is constant 4, Again, we use 300 samples and we evaluate each value, the mutual information value 100 times to get the standard deviation, which we show here. And we see that for the naive approach, when we increase the dimensionality, the error which is represented by the standard deviation is increased as well, while with using involve me, the two the green and orange lines, it is constant because of the dimensionality of x involved, which stays constant. And we also see that the smallest variance is for MSc, where we also remind that KDE was provided with perfect inference. It would be worse, I believe, when we give it a more practical inference engine. The impact of dimensionality on the time complexity is pretty similar to the accuracy. We also here see that for the naive approach, increasing the dimensionality increases the time, and we get constant time when using involve me, while MSc has the smallest time calculation time. And I believe that there is more room for improvement, because KDE was used with an optimized code, and this is and MSc is just a first implementation of ours. So to summarize, we again discussed about the problem of informative planning, where the belief space is high dimensional and the beliefs were non-parametric, and our contributions were to reduce the dimensionality for the evaluation of the rewards with non-augmented and augmented. And we also shown a way to avoid the reconstruction of future belief surfaces with MSc, and we show how we have shown how this is applicable to belief trees. And for future research, we would like to discuss to research about what happens on the focus case, where we wish to quantify the uncertainty over only a subset of the state, and also the non-parametric inference impact. For example, we know a work of an algorithm NFISM of Huang, which was introduced in 2021, and we believe it would be very relevant for the efficient and accurate non-parametric marginalization. That's it. Thank you guys for listening. Do you have any questions?
Thanks, Gilad. Thank you so much. All right. Any questions from the audience? Anyone? Last chance. All right. So let's thank the speaker again, Gilad. Thank you so much. And that's it for now. Thanks so much. Bye.
Thank you, guys.
Thanks, Gilad. Bye.
Bye.